Welcome to our discussion on area. We're going to start off with the most basic shapes to find area of, and those are rectangles. Now, of course, these are squares, but remember a square is just a special kind of rectangle. It's a rectangle where all four sides are the same instead of just the opposite sides being the same. Now, you might think of finding the area of rectangles as length times width, which is correct, but that's language specific to a rectangle. If you think of it in the more general sense of base times height, then that will help you learn other formulas for areas of other shapes, because all of these other shapes are going to have their formulas listed in terms of bases and heights. So it's nice to just kind of be consistent and think of everything in terms of base and heights. For instance, if you think of the area of a triangle, sorry, had a brain seizure there for a second, and you think of cutting this square, same thing as a rectangle, in half, you can see that it creates a right triangle, and the area of that triangle is exactly half of that rectangle, right? And the area of the rectangle would be base, right, times height. So that's why the formula for area of a right triangle is 1/2 base times height. And by calling everything base and height versus length and width, you can see that kind of family nature of these formulas, how they all fit together better. Okay, well, if you take any rectangular shape, you can always cut it up into a bunch of little squares and then count up the squares, and that gives you the area, right? So you get that orange shape, and you count it up, and if you use these little 1-unit squares, and in this case these little 1 units will be centimeters each, then you get 21 squares across, 15 squares down. If you count them all up, that's going to be the area. It's obviously going to be 21 times 15. And the other one's got 12 across, 12 down. You add them all up, there's 144 of those, and that's the area of that one. So you can always just count up the squares, but who wants to count up squares? It's much easier to just multiply the numbers. 21 times 15, get 315, and do 12 times 12, and get 144. But now you can visually kind of see why area works the way it does. So again, let's try not to do length times width and side times side. Let's just always think of it as base times height, because there's no point in thinking of a whole different formula for squares. Oh, if I have a square now, all of a sudden my area is just side squared. Yeah, it's just stupid. Why do you need to memorize a second formula when it's still just base times height? It just so happens that with a square, the base and height are the same. Okay, so let's not make our lives more difficult than they have to be. Everything is just base times height if it's rectangular. So how many square feet are there in a square yard? Well, isn't it 3 feet across and 3 feet up, right? Those little hash marks kind of mark out where the feet would be. And if you kind of connected all the lines up, and you'll have to excuse my inability to draw perfect lines, but there's your little tic-tac-toe grid, right? So 3 feet across, 3 feet down, you count them all up, there's 9 of them, right? So 1 square yard is 9 square feet. Well, that makes sense, because if you know your conversion, right, that a yard is 3 feet, if you square both sides of that equation, 1 squared is 1, yard squared is yard squared, and then 3 squared is 9, and feet squared is feet squared, right? So that's why you get 9 feet squared, or 9 square feet. So even the unit of measures makes sense, right? That they're squared. The reason why they're squared is because you've got feet times feet, or yard times yards, or inches times inches, or heaven forbid, in the metric system, centimeters times centimeters, meters times meters, and so on and so forth. All right, what about parallelograms? Well, a parallelogram is really, well, by definition, a parallelogram is just any quadrilateral, meaning it has 4 sides, and the opposite sides are parallel. That's it. That's all that it has to be a parallelogram. So you might be thinking, well, isn't a rectangle a quadrilateral with opposite sides parallel? And you would be correct, yes. So rectangles are subsets of parallelograms. They're a specific kind of parallelogram, right? A parallelogram is just a basic four-sided shape with one rule, that opposite sides are parallel. Then a rectangle adds one more rule. Not only are the opposite sides parallel, but all four angles on the inside have to be 90 degrees. And then a square, right, becomes a little bit more specific. All four sides are parallel, right? So the two opposite sides are parallel. All four angles are 90. And then we add another rule that all four sides are the same length, right? So all of these shapes are really just subsets of each other, more or less. And because of that, finding the area of them are very strongly related. Because if we want to find the area of a parallelogram, it is still base times height. The only difference is the height always has to be perpendicular to the base. So just like with rectangles, and just like with right triangles, and just like with normal triangles, we'll see later, that it's always base times height, where the height is perpendicular to the base. And it's kind of easy to see that if you took this piece here and cut it and put it over there, again, apologize for my lack of drawing skills, but can you see that those two shapes are the same, right? So you cut that off and stick it over there. Can you now see how you have a rectangle that has a base and a height? So that's why the formula works the way it works. And again, with all of these, you can very easily cut them and turn them into, and then take this piece and stick it over here. All right, and you see there's your base, there's your height, there's your rectangle. Same thing, take this piece, stick it over here. There's your rectangle, right? So base times height, just like rectangles. So now parallelograms and rectangles, same thing, same formula, base and height. So again, it's much better to do that than to think of length and width, because everything's going to be based on these base and heights. Okay, how about triangles? Well, we already saw that right triangles were really easy to visualize, that they were 1/2 base times height. What about non-right triangles? Well, we could spend some time here and we could cut this thing up and we could move some pieces around, and you would see that you can create a right triangle out of this. You can create a shape that's exactly half of the rectangle that it sits in. I'm not going to waste time doing that. You can look it up on YouTube and you can see those proofs. They're kind of nice and they're pretty. But the bottom line is, you probably already knew this. You already knew that area of any triangle is 1/2 base times height. And you could use any side for the base, right? It just, obviously the height would change. So whatever side is sitting on the ground is your horizontal piece, then the height is just the vertical distance from that base up to, the other point. So it doesn't matter which one is your base, the height just goes along with it, and it'll always be the same. It'll still be 1/2 base times height, will give you the same area, independent of which direction you rotate your triangle. Okay, so these are simple. I'm going to blaze through these really quick. You can pause and really look at the details if you want to. Now on to trapezoids. You know what a trapezoid is? Well, a trapezoid is another quadrilateral, right? So it's four sides again. So we've got to be thinking, well, our quadrilaterals are, base times height. Two sides are parallel, but the other two sides are not. And then the perpendicular distance between the two bases, the two sides that are parallel, that's called the height. Well, we can find the area of this shape basically by cutting it up and making rectangles out of it again, right? So I don't really like this picture because it gets kind of confusing with the two different triangles. Instead, I like to look at this one, because it should be very easy to see now that if you take this piece, right, cut it off, and then flip it upside down. Sorry, again, I didn't draw that really well. You can see that you now have a rectangle that is this base times this height, right? Well, is it this base? No, because we just cut this piece off, right? So what is this distance, right? So this is kind of like a little x right here, this distance x. So now this rectangle ends up being little b plus x and big B minus x. And when you do the math, it basically becomes 1/2 of the sum of both of them. So if you look at this, you can see that if we created this rectangle here, right? So here's my rectangle with this length of a base. If we cut this piece off, we can see that this is half of just this piece, and then we stick that piece over there, it fills in the gap. So that's how we're getting, right, because each of these is 1/2, right? Each of the triangles is 1/2 of something. So there's your 1/2 height times the sum of the two bases. So it's kind of like, adding the two bases is making the rectangle twice as big, and then you cut it in half to get it back down to the size of the rectangle. Because I don't know about you, when I look at that shape, it really just looks like if I cut this off, flip it, and stick it in here, I get this rectangle. And this rectangle is this height, and it's this length here. But what the heck is that length? Well, it's little b plus some amount, and it's big B minus that same amount. And when you do all the math, right, you can see the area of this first one has this base and this height. So that gives you 1/2 of this base and this height. And then the green one has this bigger base and this height. So its area is 1/2 of that. And when you put them together, and then you can factor out the 1/2 and the h, and that's where the formula comes from. So I don't know which way your brain likes to see it, but in either case, the formula is it's 1/2 height times the sum of the two bases. So it's kind of like a amalgam, right? It's kind of like a marriage between the standard old rectangle formula and the triangle formula. All right, so we can find these areas. Again, I'm going to go through them pretty quick because you guys can pause if you want to. These are pretty basic, just slapping some numbers into a fairly easy formula. Then we get to circles, and I think you're probably familiar with the area of a circle being pi r squared. So I'm not going to spend a lot of time on this. If you have the diameter, of course, you have to cut that in half, right? Because the radius is half the diameter. So if we want to do number B, or letter B, we would do 5, because it's right, that's 10. That's 10.0. I don't know what that comma is doing there, right? So 10, so it would become 5, and then 5 squared is 25, so it would be 25 pi, right? Okay, if you wanted to find area that wasn't in terms of pi, remember that you have to go ahead and use the approximation for pi, and then your answers are always going to be approximations. You always have to round at some point. All right, how about some simple applications? What if we want to convert from one unit of measure to another, and we want to do it for area? So suppose your living room is 12 feet by 15 feet, and you want to know how many square yards of carpet you need to cover this area, because carpet is sold by the yard. And when they say a yard, they mean a square yard. They just, kind of got lazy and took the square out of it. So if you do 12 times 15, you get 180 square feet. But if you want to know what that is in yards, well, you have to remember that 1 yard is 9 square feet. So 1 square foot is 1/9 of a square yard. So you multiply by 1/9 and you get 20 square yards. But you could also think of, if you just looked at these, right? A yard is 3 feet. So wouldn't you just divide this by 3 to turn it into yards? And then divide this by 3, right? To turn that one into yards. And then do you see how you have 12 times 15 all over 9 yards squared? And there's how you get the same thing, right? Because 12 times 15 is 180, and then you divide by 9. You also, of course, I'm just doing this to illustrate that that's why you're divided by 9, but wouldn't it make the math a lot easier to just do 12 divided by 3 is 4, right? 15 divided by 3 is 5, and there's your 20. Now, if your numbers weren't divisible by 3, of course, that gets a little messier, but dividing each one by 3 versus dividing the last thing by 9, it doesn't matter. It's all the same thing. It's still going to give you the same answer. So as long as you know your conversions, you're good to go. All right, what about acre? Well, again, in our silly US system, nothing seems to be normal. You know, where did these numbers come from? An acre is 43,560. Why couldn't it have just been 40,000, right? So it's just so hard to memorize these numbers. Just write them down in your notes, look them up in Google, whatever it is. But obviously, to convert now from square feet to acres, you got to divide by 43,560. So here's another example, trying to figure out how many acres are in a property that measures 363 feet by 180 feet. You could kind of approximate it and go, all right, well, that's kind of close to 400 by 200. But did you notice that we rounded both of these up a lot, right? 363, we rounded up to 400. 180, we rounded up to 200. So when we get 80,000, and then we figure that an acre, right, I said was close to 40,000, and that gives us 2, we should be thinking that that number is going to be too big because we rounded both of them up. And in fact, when we do the actual number and divide by the actual number for acres, we get 1.5 in the calculator. So you can see how it was a little bit less than our estimate because of all that rounding. Okay, so that is area in a nutshell.